In our introductory video on decision theory, we focused predominantly on a simple choice of whether or not to take a gamble. In this video, we'll learn to use decision theory and calculations of expected value to make choices that go beyond these simple gambles. By the end of this lesson, you should be able to use decision matrices to visualize decision problems. You should be able to compare non-monetary as well as monetary expected values. And you should know how to identify when a choice dominates its alternatives. We're going to start by introducing this concept of a decision matrix. The value of this is that it allows us to visualize the comparison of decisions. It helps us represent how to weigh the various choices based on their possible outcomes. In order to make a decision, we need to be able to compare the expected values of each of the choices. And those expected values come from the value of each of the outcomes, and then we weight that with the probability of each of those outcomes. So the advantage of the decision matrix is that it can help us lay out our choices. We can look at the way things might turn out once we make our choice. Those are the states. And we can see how those states and the various choices we can make affect us. That's the outcomes. So in the decision matrix, this chart here, the states are laid out across the top so that each column represents the outcomes in a different state. And the choices are laid out down the left side so that each row represents the outcomes that follow from making that particular choice. So if you want to include the probabilities of each outcome, they should be included in the box with the relevant outcome, often in parentheses next to the value of that outcome. We can then use this decision matrix as a guide to lead us to a more general formula than the one we looked at in our previous lesson video, one that tells us how to calculate the expected value of any kind of decision. So this more general formula to weight the various choices based on their values and the probabilities, the outcomes that follow from the various states. The point is that for however many possible outcomes there are, so we've listed here 2 for each choice, but that could go on, and we could have any number of possible choices to compare. We can determine the expected value of each choice depending on the possible outcomes that result from it. To get the expected value of a choice, say choice 1, we add up the products of the outcome's value and the chance of that outcome occurring for each of the outcomes that could occur associated with making that choice. For choice 1, we have outcome 2, outcome 1, and so on. There might be more possibilities. Let's look at an example of how to use our expected value formula to compare 2 choices in a decision problem. Let's say you're trying to decide whether to pay for renter's insurance. You're told that the policy is $100 a year, and the insurance covers loss of property up to $10,000 if it's due to fire or theft. The chance of a fire happening is 0.005, and the chance of a theft happening is 0.001. So here we have a matrix that gives a representation of these 2 choices. Either we get insurance or we don't. The states that affect our evaluation are either there's one of these adverse events, a fire or theft, or there's no incident. And then we have here also the values of the outcomes in each of these situations. So if we get insurance and there's a fire or theft, we only lose the cost of the insurance because the stuff we lose is paid for. But if there's no incident, we still lose the amount we paid for the insurance. However, if we get no insurance, we have to pay to get our stuff back, or we lose all of our stuff. That means incurring a monetary loss of $10,000. But if there's no incident, we pay no cost. We didn't pay for insurance. We didn't lose anything due to one of these adverse incidents. So we're just the same as we were before. Is getting insurance worth it? To determine that, we have to compare the expected value of getting insurance to the expected value of not getting insurance. Here we have the calculation for the expected value of getting insurance. The numbers at the bottom are plugged in to each piece in our formula, but the main thing to focus on is our final answer. It says that if we get insurance, we're out $100. That makes sense because what insurance does is you're out the cost of insurance no matter what happens. The benefit is that you wouldn't incur any additional loss. Now we have to calculate the expected value of no insurance. We have to multiply the value, in this case the loss, associated with not having insurance. That was our $10,000, times the chance of a fire or theft. So that was 0.006, and we got that because it's a fire or theft, and so we add those two probabilities because it's an or statement. Then we have to consider the probability that there's no incident. That's over a 99% chance. And the value to us of no incident is just 0. We don't benefit and we don't lose anything. Adding those two products together gives us an expected value of a loss of $60 for not getting insurance. To make our choice, we have to compare the expected value of no insurance to the expected value of getting insurance. In this case, the expected values are losses either way. But the lower expected loss is if we don't get insurance. That tells us that at the cost of $100, this renter's insurance is just not worth it. The chance of a fire or theft is low enough that it isn't really worth paying for the reimbursement insurance might offer in those circumstances, since those circumstances are so rare. Now, so far we've continued to focus on expected monetary value, but we can also calculate the expected value of other kinds of outcomes if we can easily assign numbers to those outcomes. So here's an example of non-monetary expected value. Say that you run a factory and you're trying to decide between two processes that allow you to manufacture widgets. Process A produces 600 widgets an hour, but it has this cost. There's a 10% chance that it stalls for 5 minutes of every hour. Process B produces fewer widgets per hour, just 540, but it has a lower chance of stalling, just 5%. Our goal is to determine which one will allow us to produce more widgets per hour. So widgets per hour is going to be our measure of non-monetary expected value. It's easy to understand that as a factory runner, you would be interested in making the choice that would maximize the number of widgets produced. And so, just like with expected monetary value, decision theory will help you choose between these two processes. So on the bottom right here, we have our decision matrix. We were told that in the cases where nothing went wrong, there was no stalling, process A produces 600 widgets per hour and process B just 540. So that's that middle column. And then we have to consider the outcomes and the chances of process stalling. So process A is a bit more unreliable. It stalls 10% of the time. And that compares to just 5% of the time for process B. Note that the numbers 550 and 495 were calculated on the assumption that the processes produce at a constant rate, and we lose 5 minutes of production. So that means losing out on 50 widgets for process A and just 45 widgets for process B. We want to calculate whether the reliability of process B makes up for its slower production rate. We can do that by calculating the expected values, the expected widgets per hour, for each of these processes. Process A makes 600 widgets per hour 90% of the time. And we have to add that to the fact that it makes just 550 widgets per hour 10% of the time. That gives us an expected value of 595 widgets per hour. Process B makes 540 widgets 95% of the time, and 495 widgets in that 5% of the time that it stalls. That gives us an expected value of 538 widgets per hour. Again, to decide between these processes, we have to compare their expected values. Since we want to produce more widgets per hour, we should choose process A. So despite the fact that process A is less reliable, it's so much more efficient, and that makes it still better. Now, we went through all the details calculating the expected values using the probabilities that each process stalled. But it turns out that in that problem, we didn't need to look at the probabilities to see that process A is better than process B. That's because whether stalled or not, process A produces more widgets per hour. This is a case of dominance. One choice dominates another when it has a better outcome no matter what happens. We can see that one choice dominates another if we look at the decision matrix and see that for the dominant choice, there's a better outcome for that choice in every column. So in our example we just looked at, process A dominates process B. If we look at the columns of the decision matrix above, we see that in every state, stalling or not, process A guarantees a better outcome. And with that, we've expanded the scope of our understanding of decision theory beyond the expected monetary value of a gamble to the expected value of a variety of quantifiable choices. And our next lesson video will take the next step, introducing an even more comprehensive concept for representing how much various outcomes are worth to us.